In this video, we're going to look at patterns that occur in single displacement reactions and synthesis reactions, and how we can use those patterns to predict which reactions will happen more easily and which ones may not happen at all. So if we consider this pair of synthesis reactions, if we assume that Na and Al are the A in the reaction, and Cl2 is the B, we can predict what the products are going to be, NaCl and AlCl3 respectively. If we take a couple quick seconds to balance both reactions, we see that we can balance them without much effort, like so. On to the actual point of this question though, how do we predict which of these two reactions is going to occur more easily? Well, we probably can't look at Cl2 because it's the same in both reactions, so let's compare sodium and aluminum. We know that sodium as an alkali metal only has one valence electron, whereas aluminum has 3. We also know that metals lose valence electrons in order to gain a complete valence shell. So, which is easier, losing 1 or losing 3? Obviously, losing 1 valence electron is going to be easier than losing 3, so that probably means that reaction 1 is more easy to happen than reaction 2. So if we put some of this into writing, we can say that losing 1 valence electron is much easier to do than losing 3. If we look to our periodic table, we can conclude that there are other patterns that we might be able to see. For example, if we see sodium, it occurs on the far left of the periodic table because it's an alkali metal, whereas aluminum is a little bit farther to the right. We also know that atomic radius is a trend that increases from right to left, meaning that sodium has a larger atomic radius than aluminum does. What does this mean for our reactions? Well, if we actually draw that out, if we show that maybe sodium's valence electron is here, that we can use as the distance to show between the nucleus and the valence electron. Now, if we compare that with aluminum's, which has a smaller radius, maybe its valence electrons would be out here, again showing that the valence electrons are less far away from the nucleus. Now, remember that the nucleus is where all of an atom's protons are, which means it is where all of the atom's positive charge is. Now, because sodium's valence electrons are farther away from its nucleus, does that make them harder or easier to lose? If you said easier, that would make the most sense, because the reason why electrons do not get lost is because the positive charge from the nucleus keeps them attracted. Now, since aluminum not only has a shorter distance from its nucleus to its valence electrons, aluminum also has more protons, which means it has more positive charge. Remember that the atomic number, 11 for sodium and 13 for aluminum, also tells us the number of protons. So aluminum has 13 protons, which means it has a stronger positive charge, which means that it's able to hold onto its valence electrons more tightly than sodium is, because it only has 11 protons instead. And because the valence electrons are farther from the nucleus, that means that they would be easier to remove, because the attraction between the nucleus and the valence electrons is weaker. So we see that this pattern and our original prediction can not only be justified by simply counting valence electrons, but by looking at nuclear charge and atomic radius. We see that our conclusion is cross-confirmed by looking at different variables. So if we put this into writing, we can say that the atomic radius of sodium is greater than the atomic radius of aluminum. Therefore, sodium's valence electrons are farther from its nucleus. And if they are farther from the nucleus, that means that they will be easier to remove, because the positive charge once again, has a weaker hold over them than with aluminums. We can look at this in a different way by instead looking at two synthesis reactions using sodium and aluminum. We know that sodium is the more reactive element than aluminum because of everything that we have looked at above. Now remember that a single displacement reaction is a reaction in which one metal or nonmetal replaces or displaces the other metal or nonmetal, whichever of the same ion type it is. Now we know that sodium is a more reactive metal than aluminum is. Therefore, because sodium is more reactive, if we ask the question, can sodium replace aluminum? The answer is probably yes, because a more reactive metal reacts with this compound more easily than the other way around. Therefore, if we were to actually write this reaction out, this reaction would actually make sense to be able to complete itself. However, aluminum is less reactive than sodium. Therefore, if we ask the question, can aluminum replace sodium? That answer would be no, because as we've seen from the synthesis reactions, aluminum is less reactive because it's harder to lose 3 valence electrons when those 3 valence electrons are closer to its nucleus compared to sodium losing 1 valence electron that is farther away from its nucleus. In short, the conclusion that we can reach is that a more reactive metal can replace a less reactive metal, but a less reactive metal cannot replace a more reactive metal. And therefore, in the case of reaction 2, I'm not going to write anything because there would actually be no reaction that occurs. From this, if we consider every metal's valence electrons, atomic radius, electronegativity, and ionization energy, we can arrange them into a trend, which is what we call the metal activity series. And the metal activity series is a shorthanded explanation that shows which metals are more reactive than which other metals. For example, all the way at the top is lithium, which makes sense because lithium is in the same family as sodium, which means it only has 1 valence electron that is able to be lost. And we also see certain patterns involving atomic radius. We know that barium, which is almost all the way at the bottom of the periodic table with 2 valence electrons, is more reactive than magnesium, which is in the same family, the alkaline earth metals, but because magnesium is higher up, its atomic radius is smaller than barium's. Therefore, because barium's valence electrons are farther away from its nucleus, that would mean that barium would be a more reactive metal. The point of the metal activity series is that when you get to the middle of the periodic table with the transition metals, this pattern becomes a little bit harder to predict, and so the metal activity series gives you a general idea about which metals react more easily compared to metals that react less easily. To conclude this video, if you can take a look at this practice problem here, we can see we have a situation that is not quite as easy to analyze as sodium versus aluminum, because barium and calcium are both alkaline earth metals, so we cannot use the valence electron argument to explain which reaction will occur and which reaction doesn't. So see if you can use the metal activity series and correlate that with your knowledge of periodic table trends and see if you can figure out whether reaction 1 or reaction 2 is the reaction that occurs, and justify which reaction will not occur based on your knowledge of the aforementioned periodic table trends.